Right, FNPC 10, here's a short on squares and cubes. We talked in class, full lesson on finding perfect squares and perfect cubes, and I showed you some strategies because it's all about understanding it without a calculator. And yes, we can use a calculator, but wouldn't it be nice to understand how to do things without it? That's what this is all about, digging a little deeper. As the math gets more complicated, the calculator becomes less and less helpful, but the concepts we learn here stay the same. So perfect squares. When we're looking for perfect squares, we're looking for two identical factors. So what you can do is you can look at a number like 729 and you can break it down into factors. So it's not even, and this goes back to our divisibility rules. There's a grade 9 video short on divisibility rules if you can't recall. But can't divide by 2. Doesn't end in an even number. Can I divide by 3? Well, 7 plus 2 is 9, plus 9 is 18. I can divide 18 by 3, so I can divide the whole thing by 3. So I get 3. 3 goes into 7 twice, 1 remainder. 3 goes into 12 4 times. 3 goes into 9, 3. So 243, well, 2 plus 4 is 6 plus 3 is 9 again, so I can divide by 3. 3 goes into 24 8 times. 3 goes into 3 once. Now 81 is 9 times 9. Now you very well could break this down again, but think you're looking for two identical factors, right? And these are the factors that make up 729. If I look at them, I have 3 times 3 times 9 times 9. Now what I'm trying to get here is I'm trying to get two groups that are exactly identical. And I have two 3s and I have two 9s, which means I put a 3 here and a 3 here, and a 9 here and a 9 here. So these things all still multiply together to give me 729, but this way I have 27 times 27. Since I have two identical factors, it means my square root is 27. So that's what you can do by breaking things down into factors. Now, what about 1089? Again, it's not even, but I can divide by 3. 3 goes into 10 3 times with 1 remainder. 3 goes into 18 6 times. 3 goes into 9 3 times. This can divide by 3. 121. 121, well, that's 11 times 11. So here I end up in a similar scenario. Can I make two groups with the same factors? I can. A 3 and a 3 and an 11 and an 11. So I get 33 times 33. So the square root is 33. So we're looking for that sort of makeup. Now for perfect cubes, we need 3 identical factors. So again, breaking them down is helpful. 1728 is even, so let's divide by 2. Good place to start. Could have divided by 4 as well, but 2 goes into 17 8 times with 1 remainder. 2 goes into 12 6 times, no remainder, and 2 goes into 8 4 times, still even. 2 goes into 8 4, and then 3, and then 2, still even. 2 1, whoops, sorry, going a bit too fast for my own good here. Divide by 2 and I get 2, and then into 3 once with 1 remainder, 216. I can keep dividing by 208. Now I'm just going to keep the 108 going, but I'm just going to make a bit more room. So I'm continuing my factor tree, but I'm just going to put the 108 up here. And I get 2 times 54, which is then 6 times 9, not 5. 6 times 9, which is 2 times 3 and 3 times 3. So what factors do I have? I have 2 times 2 times 2 times 2. So 1, 2, 3, 4 times 2, 5, 6, and then 1, 2, 3. So now, since we're looking for 3 identical factors, you're looking to see, can you split these factors into 3 even groups? You know you have 3 3s, so that's helpful. 1, 2, 3. And then here's 3 2s, so 1, 2, 3. And here's 3 more 2s, so 1, 2, 3. And if you look, that gives you 12 times 12 times 12. So 1, 2, 3 identical factors. It means the cube root of 1728 is 12. So this time we're looking for 3 groups. So what about 216? Well, 216 is even. So 2, 1, 0, 8. 254. And here we go again, 6, 9, 2, 3, 3, 3. So what do I have? I have 2 times 2 times 2 times 3 times 3 times 3. Well, again, you're looking for 3 groups with the same factors in them. And I have 3 2s, so I'll put a 2 in each group, and I'll put a 3 in each group. Now you have 6, 6, and 6, which means the cube root of 216 is 6. So you're looking for 3 identical factors. Skip to page here, because this one's really pretty cool, but it steps the difficulty up slightly. Because we've been looking for, and I'm only going to do square roots, because cube roots will get way more complicated. But I'm looking for 2 identical factors, which means I'm making factor trees, right? And we were breaking numbers down. But what if you can't find a number to divide by? Because remember that unless a number is prime, it can be divided by a prime. But like 529 cannot divide by 2. It can not divide by 3. It can not divide by 5 or 7. So you get to a point where you're just starting to try things. And that starts to get a little bit tedious, a little, I don't know, unenjoyable. So strategy. Now what it comes down to is strategy between what I call perfect centennial squares, which means 100. Because what's the square root of 100? 10. And then what's 20 times 20? Well, 400, right? And then 30 times 30, 900. Because what you're getting is you're getting these large swaths of numbers, right? The square root of any number that's between 100 and 400 is going to be between 10 and 20. The square root of any number that is between 400 and 900 is going to be between 20 and 30. And lo and behold, here we have the number 529. So it falls in this realm. So it means that if 529 is a perfect square, and you can bet it will be because I gave it to you for a reason, it means that it's going to fall between the numbers 20 and 30, which means my possibilities are, and bear with me while I write these all down, 21 times 21, 22 times 22, 23 times 23, 24 times 24, 25 times 25, 26 and 26, 27 and 27, 28 and 28, and 29 and 29, because it has to be one of those, because 529 is less than 900, more than 400. Now the key here, in order to narrow down your search, is what is the last digit of the number? Because if you rewind back to stack multiplication in, say, I don't know, grade, whatever grade, you would go, okay, 1 times 2, 2, 1 times 1, 1, and then this 1, right? 1 times 1. Then you would plug a 0 in because you're moving to your tens. And you go 1 times 2 is 2, and 1 times 1 is 1. So this column is always going to be the last number of your new number you're creating. So in this case, our new number is 9, right? It means that the back 2 numbers of your stack multiplication have to multiply to give you this number. So that really means, look at these 21 times 21, 22 times 22. The back number here, the 1 times 1, has to be 9. But 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. So this is a possibility. 4 times 4 is 16. 5 times 5 is 25, right? Ends in a 6, ends in a 5. 6 times 6 is 36, ends in a 6. 7 times 7 is 40. Ooh, 49. So this is a possibility. 8 times 8 is 64, and 9 times 9 is 81. So all of those, you know, are never going to multiply together to give you 529. So you get to this point, and you go, okay, well then it's got to be one of these two. How do I decide? Well, you can just multiply them together, or you can consider the fact that if you were struggling to divide these things, 23 is a prime number. So if 529 is a perfect square, it would kind of make sense that it's 23 times 23. Just give it a whirl. Do the multiplication, see what you get. Also, it can't be 27 times 27 because 27 is 3 times 9, which means it's 3 times 3 times 3, which means 27 has a factor of 3, which means this number would have a factor of 3 if it was divisible by 27. And that number is not divisible by 3. So you can narrow down the fact that it's got to be 23. It's a pretty cool little piece there. You might want to watch that again because there's a lot happening. But I'll do one more for you here, 1369. Now again, this number is not divisible by 2 or 3 or 5 or 7 because you can try those. But 30 times 30 is 900. 40 times 40 is 1600. And this number is in between those, which means it's anywhere from 31 times 31 to 39 times 39. Thing is, this back number is a 9. So similar to this, it means we're either going to have 33 times 33, because 3 times 3 is 9, or we're going to have 37 times 37, because 7 times 7 is 49, which gives you 9 as a back number. And in this case, all I would say is go like this. 33 times 33, well, 3 times 3 is 9, 3 times 3 is 9, block a 0, 9, 9. Well, I get 918, I get 1089. That's definitely not going to do it. Okay, what about 37 times 37? Well, 7 times 7, 49. Carry the 4, 21, 25. 7 times 3, 21. Carry the 2, 9, 11. 9, 6, 3. Look at that, 1369. And again, 37 is a prime number, which is why it'd be hard to find any other way. So it's a pretty cool way to help narrow down your search for a prime factor if it exists. That's all for squares and cubes. We got one to go on irrational numbers. So we're simplifying non-perfect squares and non-perfect cubes. And then we're going to be moving into our next section, which is graphing. So great work. Keep up the hard work. Watch these videos as much as you have to. It will come. It takes lots of practice. So keep it up, keep it up, keep it up. You're doing great.